Let's now talk about privileged roles. Trusted actors who have privileged roles in the context of the smart contract application with capabilities to deploy contracts, modify critical parameters, pause, unpause the system, trigger emergency shutdown, withdraw, transfer, drain funds, and allow, deny other actors should ideally be addresses controlled by multiple independent and mutually distrusting entities. They should not be controlled by private keys of externally owned accounts, but via multi-sigs with a high threshold, say 5 of 7, 9 of 11, depending on the criticality of the application and the value at risk. And eventually, they should be governed by a community or a DAO, decentralized autonomous organization of token holders. This is because an EOA is a single point of failure if its key is compromised or the owner is malicious. Multisig, on the other hand, brings in the security design principle of privilege separation, which is tolerant to a few of the holders being malicious or compromised. Continuing from the previous slide, when such privileged roles within smart contracts are being changed, it is recommended not to use a single step change because it is error prone. For example, in a single step change, if the current admin accidentally changes the new admin to a 0 address or an incorrect address, that's where the private key is not available, the system is left without an operational admin and the contract will have to be redeployed, which is not easy or even entirely feasible in some scenarios. Instead, one should follow a two-step approach that we have discussed earlier. The current privileged role proposes a new address for the change, and in the second step, the newly proposed address then claims the privileged role in a separate transaction. This two-step change mitigates risk by allowing accidental proposals to be corrected instead of leaving the system unoperational with no or malicious privileged role. When critical parameters of systems need to be changed, it is recommended to enforce the changes after a time delay that is coupled and logged with that logic. This is to allow systems users to be aware of such critical changes and give them an opportunity to exit from that system if they do not like the upcoming changes or adjust their engagement in any other way with the system accordingly. For example, reducing rewards, increasing fees, or changing trust models in a system might not be acceptable to some users who may wish to withdraw their funds before the change and exit. Such a time-locked execution of delayed change enforcement needs to be combined with event emission to notify users of upcoming changes via off-chain interfaces or monitoring tools. So the best practice is a time-delayed change for critical parameters that is broadcasted using events to users monitoring via off-chain interfaces. The goal is to surprise less, be more transparent and fair. As a general principle, everything in security is about being explicit instead of being implicit. Implicit assumptions, implicit trust or threat models, implicit acceptance of assets, actors, actions lead to security vulnerabilities, whereas if they are explicitly specified, implemented and documented, they can be reasoned about and evaluated from a security perspective. Even with the Solidity language, it has progressively adopted explicit declarations of intent over the versions, such as with function visibility and variable storage. So it's recommended to do the same at the application level, where all requirements should be explicitly specified so they are accurately implemented and lend themselves to validation. Implicit requirements, specification, and implementation assumptions should be explicitly documented and validated for correctness. Any latent implicit requirements and assumptions should be flagged as being dangerous. Security issues arise not only from implementation errors but also from misconfiguration of system components such as contracts, parameters, addresses, and permissions, all of which may lead to security issues. Such configuration aspects should be documented and validated. Test configurations should be clearly marked as such and separated appropriately from production configurations. This is critical because testing is typically done with lower thresholds of different values to allow for faster or easier testing. They may also use more acceptable trust models or lower levels of threat than what is really encountered in a production setting. So the best practice is to check configuration settings and make sure that they are correct, relevant, and validated for a production deployment. Lack of initialization. Initializing with incorrect values or allowing untrusted actors to initialize system parameters may lead to security issues. This is especially true for critical parameters, addresses, permissions, and roles within the system because the default or incorrect values may be used to exploit the system, either technically or economically. The best practice, therefore, to avoid security pitfalls from initialization is to check that it is done and done correctly using the right values and done so by only the authorized users. Missing the cleaning up of old state or cleaning up incorrectly or insufficiently will lead to reuse of stale state, which may lead to security issues. Cleaning could be in the context of using Solidarity's delete primitive or even simply reinitializing variables to default values in the context of the application's logic. For example, this is applicable to contract state maintained in state variables within storage or even local variables within contract functions where old stale values may lead to incorrect reads or writes in the context of the contract's logic. Cleaning up storage state using delete primitive provides gas refunds with an EVM, some of which has changed in recent upgrades. London upgrade, for example, reduced gas refunds of S stores. Nevertheless, there are benefits besides security to this aspect of cleaning up. At a very high and perhaps abstract level, data processing issues may lead to security issues. In the application logics context, this could arise from several reasons, such as while processing critical data or from processing of tainted input data. Processing could be missing or incorrectly implemented. This could either result from a faulty specification or implementation without being caught during validation. Therefore, all aspects of data processing should be reviewed for potential security impact. A specific aspect of data processing that we just discussed is data validation, where contract functions check if the received data from external users or other contracts is valid based on aspects of variable types, low or high thresholds, or any other application logic specific context. Validation issues very frequently lead to security issues. Missing validation of data or incorrectly, insufficiently validating data, especially tainted data from untrusted users, will cause untrustworthy system behavior, which may lead to security issues. Sanity and threshold checks are therefore critical aspects of data validation. Another specific type of data processing is numerical processing, where the logic operates on numerical values. Incorrect numerical computation will almost always cause unexpected behavior, some of which may lead to serious security issues if not accounting miscalculations. These may be related to overflow, underflow, precision handling, typecasting, parameter return values, decimals, ordering of operations with multiplication division, and loop indices, among other things. The recommended best practice is to adopt widely used libraries for special mathematical support, such as fixed point or floating point numbers, and combine this with extensive testing using fuzzing and other tools meant to specifically test constraints and invariants for numerical issues. Another specific type of data numerical processing is that related to accounting. Incorrect or insufficient tracking or accounting of business logic related aspects such as states, phases, permissions, roles, deposits, withdrawals of funds, mints, burns, transfers of tokens, or rewards, penalties, fees within DeFi applications. All these may lead to serious security issues, and we have seen numerous vulnerabilities specifically related to this aspect. Therefore, accounting aspects related to application logic, states, or transitions, or numerical aspects, as outlined earlier, should be carefully reviewed to make sure they are correct and complete. We have discussed this multiple times, but this aspect of access control warrants revisiting again because it's central and critical to security. Incorrect or insufficient access control or authorization related to system actors, roles, assets, and permissions may certainly lead to security issues. Therefore, the notion of assets, actors, actions in the context of trust and threat models should be reviewed with the utmost care to avoid such security issues. Recording or accessing snapshots or logs of important events within a system is known as audit logging, and the recorded events are called audit logs. Note that this auditing from a logging perspective is different from the concept of external reviews, which is also called auditing. Auditing and logging are important for monitoring the security of an application. In the context of smart contracts, this applies to event emissions, the ability to query values of public state variables, exposed getter functions, and recording appropriate error strings from requires, asserts, and reverts. Incorrect or insufficient implementation of these aspects will impact off-chain monitoring and incident response capabilities, which may lead to security issues. Correct and sufficient audit and logging is therefore something that also needs to be paid attention to for reasons of monitoring, detecting, and recovery aspects of security. We have discussed cryptographic aspects fundamental to Ethereum in the earlier modules. Incorrect or insufficient cryptography, especially related to on-chain signature verification or off-chain key management, will impact access control and may lead to security issues. So aspects of keys, accounts, hashes, signatures, and randomness need to be paid attention to, along with the fundamental concepts of ECDSA signatures and Keccak 256 hashes. There are also other deeper and newer cryptographic aspects one will encounter in Ethereum applications or protocol upgrades, with abbreviations such as BLS, RANDAO, and VDF, and also zero knowledge aspects. I would recommend looking these aspects up if you're interested in cryptography and their applications to Ethereum. But at a high level, cryptography is fundamental and critical to security. And even a tiny mistake here can be disastrous, surely leading to security vulnerabilities. We discussed error reporting briefly under auditing and logging, but let's revisit it here. Incorrect or insufficient detecting, reporting, and handling of error conditions will cause exceptional behavior to go unnoticed, which may lead to security issues. At a high level, security exploits almost always focus on exceptional behavior that is normally not encountered or validated or noticed. Such exceptional behavior is what is anticipated, caught, and reported by error conditions, and any deviations from the specification are errors that should be detected, reported, and handled appropriately by the implementation. Denial of service, or DOS, is also a security concern. Traditionally, security has been considered as a triad, referred to as CIA, which stands for confidentiality, integrity, and availability. DOS affects availability, and in this case, that of the smart contract application. Preventing other users from successfully accessing system services by either modifying system parameters or shared state causes denial of service issues, which affects the availability of the system. The effects of this could cause users to have their funds locked, reduce profits, prevent from having their transactions included, and therefore interactions with the contracts denied. Attackers may cause DOS without any apparent or immediate economic benefits to themselves, and do so by spending Ether on the gas or any other tokens required for such DOS causing interactions, which is typically referred to as griefing. So the best practices here are to recognize and minimize any such attributes in the smart contracts or application logic that could enable DOS. Timing issues can have a security impact. Incorrect assumptions on timing of user actions which cannot be controlled, triggering of system state transitions, or dependencies on blockchain state blocks transactions may all lead to security issues depending on the application logic context. Therefore, any timing attributes or logic within smart contract applications should be analyzed to check for such issues. Similar to timing issues, incorrect assumptions on ordering of user actions or system state transitions may also lead to security issues. For example, a user may accidentally or maliciously call a finalization function or other contract functions even before the initialization function has been called if the system allows this to happen. Attackers can front-run or back-run user interactions to force assumptions on ordering to fail. Front-running is when the attackers race to finish their transaction or interaction before the user. And back-running is when they race to be behind or right after the user's transaction or interaction. Combining these two aspects can also be exploited in what are known as sandwich attacks, where the user's transaction or interaction is sandwiched between those from the attacker. So the best practice is to pay attention to the related aspects of timing and ordering attributes and evaluate if they can be abused in any manner. Undefined behavior that is triggered accidentally or maliciously may lead to security issues. But what is undefined behavior? Any behavior that is not defined in the specification but is allowed either explicitly or inadvertently in the implementation is undefined behavior. Such behavior may never be triggered in normal operations, but if they are triggered accidentally in exceptional conditions, that may result in rewards. However, if such behavior can also be exploited in some manner, that leads to security issues. In some cases, it may not be clear if such undefined behavior is a security concern or not, but nevertheless should be treated as such. The best practice is to make sure all acceptable behavior is detailed in the specification, implemented accordingly, and documented thoroughly. External interactions can have a security impact. Such interactions could be with assets, actors, or actions that are outside the adopted trust and threat models and hence external. Interacting with such external components, for example, tokens, contracts, or oracles, forces the system to trust or make assumptions about their correctness or availability, which requires validation of their existence before interacting with them and any outputs from such interactions. Therefore, such external interactions can have security implications and need to be considered carefully. Increasing dependencies and composability make this a significant challenge.